Hello together. We are in the middle of the section on the spectrum of certain bounded linear operators acting on Banach spaces. At this point, we know the basic definitions. We have assembled some results, mostly about, well, resolvent set being open, spectrum being compact, a spectral radius formula that we proved last time, and there will be one more general result coming up very soon, but at this point it is time for another example. So we had one example up front. This was the right shift that we solved without knowing any general theory. This was just based on the definitions. And now with this one here we can do much better, much faster. Namely, this is the following example. So we're going to look at the space of square summable sequences. So that is a Hilbert space with the ordinary inner product. Here the scalar field will be the complex number field. This you have to specify in problems on the spectrum because well, the spectrum and the resolvent set are subsets of the underlying scalar field. So you have to tell up front which scalar field you're choosing. And the operator we're interested in is an old familiar one, namely the multiplication operator. That guy we got to know in the very first week of this module. Here's just to remind you, so for a given bounded sequence T, what the operator capital T does, well, it takes a sequence and then multiplies each entry with the corresponding entry in the sequence small t. All right, we know a few things about this guy. We know it's linear. Bounded operator, we computed the operator norm. It is precisely the L infinity norm of the sequence that you multiply with. And now what we will do is, well, answer the typical questions, compute the resolvent, the spectrum, and the various components of the spectrum: point spectrum, continuous spectrum, and residual spectrum. All right, so here notice I've made one assumption up front. This is for non-triviality, so I assume that the sequence that I'm multiplying with is not identically zero, because if that guy were identically zero, the spectrum is just one point, namely the origin. You will see this, and this is super trivial, so let's not bother about this case. All right, so with this assumption in place, then indeed the operator norm is strictly positive, and I abbreviate it as small r. All right, now using what we have learned over the past videos, so first of a general fact is that then the spectrum, remember the spectrum is always bounded, it is closed, hence compact, and moreover it is sitting inside a disk centered at the origin with radius at most the operator norm, right? So here we already know that the spectrum will be sitting inside a closed disk of this radius small r, which is the L infinity norm, and that thing has to be closed, right? And there again, you see why r should not be equal to 0, because then it's just, you know, then if r were 0, you would be done with this example at this point, right? Because then the spectrum is just the origin. It cannot be empty, because we had a result that if you're over a complex Banach space, the spectrum is non-empty. All right, good. So now let's move on. Again, as I said in the last example, there's not really a gold standard here how you get to the finish line fastest. I usually prefer to look at the point spectrum first, so eigenvalues, eigenvectors. So I will do the same again. So let's look at the eigenvalue, eigenvector equation. You apply it, and this is pretty easy to see what it means coordinate wise, so then, or component wise rather, than for all k in n, the eigenvalue equation is just tk minus lambda xk equal to 0, and 0 here, this is now the scalar 0. All right, this is your eigenvalue equation. This you get immediately from the definition of the action of capital T. All right, so now you have to satisfy this. I already factorized it. I got this one bracket here, tk minus lambda, and I got the second factor xk. And this has to hold for all natural numbers k, right? So now, of course, the choice that you don't want to make is that you set all the xk's equal to 0, because that would land you on the 0 sequence, and that's forbidden as an eigenvector. Remember, eigenvectors are always non-zero vectors. All right, so now I claim this equation yields the following eigenvalue eigenvector pairs, right? Which yields the eigenvector eigenvalue pairs eigenvector, eigenvalue pairs. X is En and lambda is Tn, n1 infinity. So the En, this is our favorite guy, so En is Enk, k1 infinity, and Enk is 1 when k is equal to n and 0 otherwise. All right. And what I claim is that E sub n for any natural number n is an eigenvector with corresponding eigenvalue lambda is equal to Tn. So how can you see this? Well, you got to look at this equation, of course, the eigenvalue eigenvector equation. And remember, I don't want that all the xk's are equal to 0. So suppose one of that xk is non-zero without loss of generality equal to 1. Right, but then it means that for the same index k, the first factor has to be equal to 0, right? And that's precisely what this guy here does. Lambda is equal to Tn, right? So these are certainly eigenvector eigenvalues that you can check. But now what I claim is actually that there's no others. So I claim that the whole point spectrum is equal to, well, those Tn's. Okay. So we have convinced ourselves, or I tried it in words, that certainly the Tn's are contained in the point spectrum, but why is there nothing else? Well, this is again coming back to the red underlined equation, right? So the lambda here, it cannot change. Lambda is a scalar, right? So lambda equal to tk is one possibility here, of course. And then you can choose the xk freely. But if you were to choose a different choice for the entry, remember xk is the coordinate in the sequence x, then you would not be able to satisfy this eigenvalue eigenvector constraint. The only solution of the red underlined thing is indeed this one, right? Even if in your sequence the tk, some of the tks, they might be equal to one another. For instance, t1 might be equal to t2, right? Then of course you could choose an eigenvector which has a 1 in the first entry and a 1 also in the second entry. Yeah, but that is a linear combination then of En and of E1 and E2, right? So it is still going to be sitting in this collection. So you're not going to generate any other eigenvalue eigenvectors there anymore, right? Good. Good. So then this is indeed what we get for the point spectrum. All right. Next. So now in this example, I diverge slightly from what I did in the last one. So in the last one, we played around with the Neumann series and got some information, then went to the dual operator. Not the dual, the adjoint. Now here we can actually do this quicker because sometimes one is able to compute the resolvent operator explicitly. And here is one case where you can do this, right? So I claim so that the resolvent r lambda of t acting on x, this will be a sequence, and then I will write out what the nth entry of that sequence is. I claim it is the following thing, xn over lambda minus Tn for all lambda. Well, I shouldn't be dividing by 0, so I have to stay away from the Tn's, right? Okay, and x is an arbitrary element in L2, in L2n. Okay, so we compute, next defining this for all and this, we compute. That's an easy computation. That's the check that this thing does what I wanted to do. So if you compose r lambda t with this, I claim, maybe let's write the claim and then I will explain why it is true. R lambda of t, lambda I minus t. Okay, so why is this? Now, yeah, okay, look at, for instance, the left-hand side. Act with an x on it. R lambda tx. So this guy will be, well, according to my definition, at the nth entry, so it will be x1 over lambda minus t1, x2 lambda minus t2, all the way there, right? So this will what the sequence look like. And now I act with that guy from, I act this guy on lambda I minus t from the left. So lambda I minus t, what does it do? Well, it just multiplies, because t is multiplication operator, So let's write it like this. So what you will find out here is would multiply each entry by, well, first one, lambda minus t1, x1, lambda minus t1, lambda minus t2, x2, lambda minus t2, and on and on and on. Okay, and then provided lambda is different from all those tj's, then you can divide out these guys. And so what you get here is, at least for the left-hand side, I've shown it now, the computation for the right side here, this guy here is absolutely similar. You get indeed the identity. Okay, so that way our lambda up there is a good candidate for indeed the resolvent, right? Because it satisfies, it's both a left-sided inverse and a right-sided inverse. Yeah, but we also have to verify maybe the boundedness. So let's look at this. So this is an equation valid on L2n, all right? And we also estimate, that's easy. So the operator norm, I claim, cannot exceed 1 over the distance of lambda to all your tn's. Okay, so why is this? Okay, let me write this out. So if you look at r lambda tx and you do a 2 norm on this, by the way I have defined it, then this would be k1 infinity. Oh, let's do n. Let's do a square here, and then it would be xn squared, and then lambda minus tn squared, right? So now what you can do is you can easily estimate this guy down here by saying, well, this is at least the distance between lambda and any of your tn's, right? And that way you can remove the green bubble outside, and what you have left here is 1 over the green stuff, and then what is left is simply, well, the green stuff, there's a square here, right, because there's a square up here, so it would be distance, oh sorry, in green, it would be distance squared, and then what you have here is just the 2 norm of this guy squared, right? So, and then now, since this is valid for any x, you optimize over the boundary of the unit ball in L2, and then indeed you immediately find out this estimate up there, all right? So that's clear, that's how you get this, all right? So now what can we conclude from this? Thus I claim. So we have the resolvent is the complement of the spectrum, right? So this resolvent up there, it certainly exists, or I shouldn't call it resolvent yet. This guy here certainly exists in L2 for all values of lambda which are not in here, right? And I have this estimate, right? Because resolvent has to be bounded, has to be a bounded operator. But now look, what might happen is, of course, if that sequence of your tn's has a limit point, right? So the tn's could be, for instance, 1 over n. That's certainly a bounded sequence. But now when n becomes large, that sequence is going to creep up to 0, right? So, and to have this bound up here, you want this to be finite. Your lambda should stay away, of course, then from that limit point. Otherwise, it's going to explode here and you would have an unbounded operator. That's not allowed in this class, right? So in other words, the resolvent here is the complement of the spectrum and thrown in all the limit points, right? So in other words, what I have to write here, this is Tn like this, and then the closure of this guy. So all the limit points of this sequence, okay? And that is the resolvent, all right? And we just proved it. And so, well, the spectrum would just be the complement of this. This would be Tn, infinity, and the closure thereof. All right, good. So I already know that the point spectrum is all those Tn's without the closure. So now what remains to be seen is whether the limit points are either in the continuous spectrum or in the residual spectrum. Right, so let's do this now. All right, so But this is easy. Maybe let's move this up here. Let's move this up here. Why is it easy? Well, because we know something about the multiplication operator. So recall that t is normal. But on that day when I defined normal operators, self-adjoint operators, and unitary transformations, we did precisely the example of the multiplication operator. And we figured out it is always normal, it is self-adjoint if all those tj's are real, and it is unitary if the gj's in complex modulus or absolute value are equal to 1, right? So I already know that this guy is normal, right? Hence, the very first result in this section on the spectrum was saying that the kernel of lambda I identity is the same as lambda bar I minus the adjoint of t. More precisely, the first result in this section was this statement. Tx equal to lambda x, x different from 0, if and only if t star x equal to lambda bar x, right? And if you translate this over into the kernel language, then it's precisely this blue equality between the two kernels, okay? This was the very first result in this section, right? So let's erase it. Yeah, but now since I have this, thus, using that we are in a Hilbert space, the projection lemma kicks in, so you have the existence of complementary subspaces, and this argument we already used once before. So what I'm going to do is I'm going to use the following subspaces. I'm going to use the range of this one and the closure thereof, yes, and then here would be just applying the projection lemma, lambda I minus t star, right? So if you want it in full generality, the statement about the complementary subspaces is that if you are on a Hilbert space and you got a bounded linear operator, then the kernel and the closure of the range are complementary subspaces. And here I use this statement not for t, but for lambda I minus t. Okay, that's what I have. And they're complementary in the sense that the intersection of that kernel here on the left with the range on the right with the closure on top is just a zero vector space. Okay, so now we have this, but I already figured out that that kernel here is just the kernel of lambda I minus t plus range lambda I minus t. Okay, good, right? All right, in turn, if you are in the residual spectrum, if lambda were a value in the residual spectrum, then it is not an eigenvalue. That means the kernel is trivial. So, kernel lambda I minus t is just a zero vector space, and the range is not dense. Right? This is what the residual spectrum does. But now you have a contradiction, right? Because the projection lemma says that the kernel, which is now here the zero vector space, plus that closed up range has to be all of L2, right? But here, if I were in the residual spectrum, that would not be the case, so I have a contradiction. Hence, there are no elements in the residual spectrum. A contradiction. So residual spectrum is empty, right? And so then we are left with what? The continuous spectrum. This is the complement of that closed thing minus, well, all the elements in your sequence. Okay, that's it. All right, that's it. So exploiting this fact here, the projection lemma in a Hilbert space, can quickly get to the finish line. And the only thing that we used here is that we're actually dealing with a normal operator, okay? We didn't use the precise structure here anymore. In this part here, starting from here on, we did not use the precise form of our operator anymore. Only the fact that it has a built-in symmetry, which is the normality, okay? So that in turn, of course, now will mean, and this is summarized in the upcoming result, that if you have a normal operator on a Hilbert space, the residual spectrum will always be empty. Okay, good. And indeed, this is what I formulate here in the upcoming result. So this is a very important thing. Whenever you're on Hilbert spaces and you get a problem asking you to investigate the spectrum, first ask yourself whether the operator has some symmetries, right? Because then your life is much easier. Namely, if you have a Hilbert space, bounded linear operator thereon, and if your guy is normal, then the residual spectrum is empty. So you don't have to do any more work now that you have this theorem. If the guy is normal, you can just write residual spectrum is empty. If it's unitary, well then of course residual spectrum also has to be empty, because unitary operators, U star, U star, U, they are of course normal, and likewise self-adjoint ones are normal, right? So that's why it's no surprise once you know this here on top, you get in number 2 and number 3 that the residual spectrum is empty for free. All right? But 2 and 3 say more. They say if you're in the unitary case, then the spectrum is a subset of the of this set. So if the scalar field is the complex plane, then this would just be the boundary of the unit disk. If you are on the real line, then it's either plus or minus 1, right? And this statement says the spectrum is a subset of that. Right. Now, number 3, if you're in a self-adjoint case, the claim is then, well, the whole spectrum is real. And this is a vast generalization of what you know from linear algebra. If you have Hermitian matrices, that's what I said, this is kind of what corresponds to the self-adjoint operators on the finite dimensional vector space. Then linear algebra says that all the eigenvalues have to be real. So in particular the point spectrum, but here the statement is much broader, because it says not just the point spectrum is real, but all of the spectrum is real if you have a self-adjoint operator on a Hilbert space. All right, so this is a great theorem, and now we will prove it, or at least in the remaining minutes a few parts of it. So proof, well, that guy with normality, residual spectrum empty, this we already did. So we know that by the projection lemma H is kernel. Let's write it one more time. Lambda I minus this plus the closed range of this. And then since you are in the normal situation for normal t, then this guy, the first one, is just lambda I minus t plus range lambda I minus t that you close up. And they are complementary, right? So that means plus, oh, not in green maybe, plus complementary. So the intersection of these two guys is 0. Okay? Consequently, if lambda is where in the residual spectrum, then by definition, kernel lambda I minus t, because points in the residual spectrum are not eigenvalues, that would be the 0 vector space. So this first piece here would be gone. But also in the residual spectrum, the range is not dense, and then you have a big contradiction to this equation here. All right, and range lambda I minus t not dense. All right, a contradiction. Thus, sigma r t is empty. And then I explained it while I was reading through the statements, having established this, that in the normal case, the residual spectrum is empty. You get then for free that in the unitary, in the self-adjoint case, the spectrum, the residual spectrum is also empty. All right, so now we only have to prove a few more parts. Maybe let's do the unitary one. Moving ahead, if t is unitary, then, well, okay. So one of the properties after we had defined the adjoint was this property that the operator norm of the adjoint with itself is just the square of the operator norm of t. But if you have a unitary t, then the product of the adjoint with t itself is the identity. So this guy is equal to 1. So in other words, the operator norm being non-negative, the operator norm of a unitary operator is equal to 1. Thus, remember, the spectrum is always contained in a disk of radius at most equal to the operator norm. So that means already that the spectrum is sitting inside, well, that unit disk in the complex plane if the field is the complex number field, or that unit interval from -1, 1 if you're on the real line. All right, good. But any unitary operator is invertible, by definition. Any unitary operator is invertible. So certainly 0 is in the resolvent set, right? Because that's the set for which lambda I minus t is invertible. But if lambda is equal to 0, then you just have the statement that minus t, equivalently t, is invertible, right? So 0 is certainly in the resolvent. And if 0 stays away from the boundary of the unit disk, or that interval if you're on the real line, then here's a little trick. Lambda I minus t you write as minus t I minus lambda t star. This is valid because, well, t star is equal to t star t star is equal to the identity. Okay, now this guy here on the left is invertible, that we already discussed. And now why is this one invertible for all lambda in here? Well, because of the Neumann series, right? So Neumann series is if you have this here less than 1. Well, okay, let's do it one step at a time. So first off, this is precisely equal to lambda like this, but the operator norm of the adjoint is equal to the operator norm of t itself, and t has operator norm 1, right? So this is precisely lambda in absolute value or complex modulus here, but this is strictly less than 1 by this line here, right? So, and that's why by Neumann series also this factor is invertible, all right? So in turn, what this tells us is, this shows lambda I minus t is invertible for all 0 lambda less than 1. So we must have, that means that open disk is in the resolvent set. So then the spectrum has to be in the closed disk, but the open disk is in the resolvent set. So that means the spectrum must be a subset of the boundary, right? That's the only thing that is left. Okay, excellent. So now what remains is the part about the self-adjoint operators, which we will do in the next video. I'll see you then.